Hey everyone, so we're going to start on section 3.7, which is titled Chemical Reactions and Chemical Equations. We have to learn how to start reading these things and understanding what they mean. First of all, in a chemical equation like the one I'm showing you here, this is the formation of water. You have to have conservation of mass. Okay, so what that means is that everything that you have on one side of the arrow, okay, one side of the chemical equation, you must have on the other side. Okay, so the number of things, molecules, atoms that you have must be the same on both sides. We're going to learn how to do that very carefully later on when we start balancing these equations. Alright, so the stuff on the left, the stuff that is going to react together, are called reactants. The stuff on the right are your products. That's what happens after the reaction. So the way that we would read this is 2 molecules of hydrogen react with 1 molecule of oxygen to yield 2 molecules of water. I want you to pay attention to the difference between coefficients and subscripts. Alright, so coefficients tell you how many of that molecule you have. So you have 2 moles of diatomic hydrogen, 2 moles of H2. You have 1 mole of diatomic oxygen, 1 mole of O2. And then on the right, you have 2 moles of water. We went over this in class, so this shouldn't be new to you. And of course, the subscripts just tell you how many of those atoms you have. So you have 2 moles of oxygen, and you have how many moles of hydrogen atoms. So we would have to take the 2, which is the coefficient, times how many of those hydrogen atoms we have. That would equal 4 hydrogen atoms. But you only have 2 moles of diatomic hydrogen. There's a little bit of a trick there in understanding what you're reading. Make sure you understand that. So on the left, we have a total of 4 hydrogen atoms. So look on the right. On the right, we also have 4 hydrogen atoms, which makes sense. On the left, we have 2 oxygen atoms, okay? And on the right, we also have 2 oxygen atoms because this oxygen here gets multiplied with the coefficient in the front. When we balance equations, all we touch are the coefficients, the big numbers, not the subscripts. Okay, let's talk about that a little bit more now. So here I'm showing you an unbalanced equation. This is the decomposition of potassium chlorate. Potassium chlorate decomposes to yield potassium chloride plus oxygen gas. If you notice, the only thing that's unbalanced here is the oxygen, because we have 1 mole of potassium on the left and the same on the right. We have 1 mole of chlorine on the left and we have 1 of chlorine on the right. But then the oxygen has 3 moles of oxygen atoms on the left and the 2 moles of oxygen atoms on the right. The way that I do this is I like to set up everything as a table. I like to write down what we have on the left and what we have on the right to make it easier for me to visualize how to balance it. So on the left, I have 1 potassium. On the right, I have 1 potassium. Good. On the left, I have 1 chlorine. On the right, I also have 1 chlorine. And now the oxygens are what's different. On the left, I have 3. On the right, I have 2. So what can I multiply both of those things to get an equal number of atoms? So if I multiply the left by 2, right, so 3 times 2 would give me 6, all right? And then if I multiply the right by 3, 2 times 3 would give me 6. So I can put that 2 as a coefficient in front of potassium chlorate. That, of course, would change the amounts of chlorine and potassium that I have as well. So we have to denote that. Now, if I put the 2 in front of the potassium chlorate, that means I've changed my potassium atoms to 2, and I've also changed my chlorine atoms to 2. So I have to take care of that in the other side as well. But first, let's go to the oxygen. We said that if we multiply the oxygen by 3, we would get 6 oxygen atoms. So that way, the both oxygens would balance on both sides. So let's do that. Let's put the coefficient of 3 in front of the oxygen. Now we have 6 moles of oxygen. Beautiful. But remember, we've got the 2 potassiums and the 2 chlorines that still need to be balanced. So why don't I just put a 2 in front of the potassium chloride? And now you can notice in your little table that you've made, everything matches. You've got 2 potassiums on the left, 2 potassiums on the right, 2 chlorines on the left as the same on the right. You've got 6 oxygens on the left, and you also have 6 oxygens on the right. So balancing equations is not hard. It's just it's a trial and error. You have to go back and forth. There are some tricks that you could use, and I would suggest that if you have atoms that are in 2 different molecules that appear twice on either side, I would leave those for last. Okay, I would try to take care of the ones that are easy first and then leave the hard ones for last. Let's try another example. It reads, the reaction between iron 3 oxide and carbon monoxide to yield iron and carbon dioxide. And yes, there are no molecular formulas here. You have to start learning that nomenclature because this is the way that the problems are going to be from now on. So, iron 3 oxide, we should know, is Fe2O3. Carbon monoxide is CO. And that yields iron by itself plus carbon dioxide, which is CO2. You set up your little table and you see that you have 2 irons on the left, 1 iron on the right. You have how many oxygens? Well, you have 3 plus 1 because of the carbon monoxide. There's an oxygen as well. So you have a total of 4 on the left and you have only 2 on the right. And then carbon, 1 on the left, 1 on the right. See if you can balance this equation. All right, good luck. Section 3.8 talks about amounts of reactants and products. This is a figure in your book. It's on page 97. It's figure 3.8. I would suggest that you become really familiar with this figure. So oftentimes in a laboratory, the question will arise, like, how much product did I form from the specific amounts of whatever starting materials that I made? So this is how you would figure that out. Okay, and this is called stoichiometry. Stoichiometry is basically the quantitative study of reactants and products in a reaction, in a chemical reaction. And we're going to do stoichiometry using the mole method, which is great because we already know how to work with moles. So, for example, you would start out with a balanced chemical equation, which we know how to balance chemical equations now, and you would convert everybody into moles. Okay, if they don't give you the moles to begin with, you would convert everybody into moles. We know how to do that using the molar mass. From the moles of whatever, moles of A, you would go to moles of B, whatever other compound that they want. And then you would go from the moles of B and find whatever unit they're looking for. It sounds really confusing right now, but we're going to do an example and you're going to see what I mean. This is really easy, and we already know the basics of this because we've studied how to get from grams to moles, how to go from moles to atoms. We've done all of this. All we're doing now is just introducing a chemical reaction in the mix. This is practice exercise 3.13. It says methanol burns in air according to the following equation. We read 2 moles of methanol react with 3 moles of oxygen gas to yield 2 moles of carbon dioxide plus 4 moles of water. So the actual question says, if 209 grams of methanol are used up in a combustion process, what is the mass of water? So basically, if you remember the figure that I just showed you, that tells you the path. They give you the grams of A, and for you to get to grams of B, because that's what they want the mass of the water, all right, that would be your B, you have to go through moles first, all right? So we would do 209 grams of methanol. How do we get to moles of methanol? Molar mass. From the molar mass, then we have moles of methanol. That's your moles of A. Then you go to moles of B, all right? So in this reaction, 2 moles of methanol yield how many moles of water? 4. So that ratio you would put is 2 moles of methanol yields 4 moles of water. Now you have the moles of your B, right? The moles of water on the top. But that's not what they're asking. They're asking for what is the mass of water. So how do you get from moles to grams? We know that, molar mass. So you would put how much does water weigh? Water weighs 18 grams, but of course that would go on the top. So you would say that in 1 mole of water on the bottom is equal to 18 grams of water. And you would just multiply all that out and get your answer. All of these stoichiometry problems follow the same format. You have to go from whatever unit they give you, whether it be grams, atoms, whatever, but convert it to moles, because remember what I said, moles is like the intersection. You can get anywhere with moles. So you got to get from grams to moles, or whatever unit they give you, grams, atoms, molecules, to moles of A. And then take that moles of A and use the mole to mole ratio to get to moles of B. And then finally, convert moles to whatever other unit that you need to go to get the final answer. One thing I forgot to mention is that whenever you do these stoichiometry problems, you must make sure that the chemical reaction you're using is balanced. Because if it's not balanced, then your answer will be wrong. So that's the first step of stoichiometry problems, is making sure that the equation they give you, don't take it for granted. It might not be balanced. So make sure it's balanced. If it's balanced, then you go ahead and you do your normal path. Grams to moles of A to moles of B to grams of B. Only other thing that's left in this chapter is limiting reagents and reaction yield. Those are two easy concepts. I am going to make a very short video going over those very quickly. All right, see you later.